Let's practice finding the electron configuration for tin. In this video, we'll find the electron configuration and the noble gas configuration for tin, whose abbreviation is SN. So starting with the electron configuration, let's go through and see the different blocks of the periodic table. So on the left-hand side, we have the S block with the first two columns. On the right-hand side of the periodic table, we have the P block. Our transition metals make up the D block. And then down at the bottom, we have the F block, which we won't need to use for this video. So let's start with energy level 1. And even though helium is on the right-hand side, it belongs to the S block. So we can write this as 1s2. Then going down to the second energy level, we have 2s2 and then 2p6. And then going down to the third energy level, we can kind of repeat what we have here. So 3s2, 3p6. And then the fourth energy level is where it gets a little tricky. So first we have our 4s2, but then it's our first time having anything in the D block. But our D block is lower in energy, so we'll write this as 3d10. And then we can continue on with our P block. So that's still 4p6. And then we'll go to our fifth energy level, and this is where tin is located. So we can repeat that same pattern as the fourth energy level with 5s2, 4d10, and then 5p2. So now, if we were to do our noble gas configuration, we need to find the closest noble gas that we've already passed. In this case, it would be krypton. And so in brackets, we can put Kr, and then since Kr is an energy level 4 and it's P6, we can include all of this in that bracketed area. So that's all taken care of. And now we can finish off our electron configuration with 5s2, 4d10, 5p2. This problem asks us to think about which element has the largest atomic radius. So not ionic, just the atomic. So we can look at the periodic table and think about our periodic trends. So from left to right across the periodic table, we can tell that the atomic radius will decrease. And this is because as we add more electrons as we go across the periodic table, they're held more closely to the nucleus. As we go down the periodic table, we're adding more energy levels. So that will increase the atomic radius because we have more energy levels. So let's identify which elements we have. We have lithium, sodium, rubidium, fluorine, and iodine. And we can see that we want something on the bottom left of the periodic table. So our final answer should be rubidium or C. For this problem, we need to decide which term best describes the following series of elements. So we can identify them on the periodic table. They are manganese, iron, cobalt, nickel, and copper. And we can see that these are located in what we call the D block. So when we look at our response options, we see that the first option best represents the series as A, D transition metals. This question wants us to find the ground state electron configuration for arsenic, whose abbreviation is AS and is element 33 on the periodic table. So we can go through and write the electron configuration using each energy level. So we have N equals 1, N equals 2, N equals 3, and N equals 4. So let's go through and write out our ground state electron configuration for arsenic. So starting with 1s2, because helium actually comes over to the S block, we have 1s2, and then for energy level 2, we have 2s2, and then we have a full P block, so we can write 2p6. Then moving on to energy level 3, we again have a full s block, so we can write 3s2, and we have another full p block, so 3p6. Continuing on to energy level 4, this is where it gets slightly trickier. So we have the full s block again, which is 4s2, but then we have the d block, and we need to remember that the d block is lower in energy, so we will actually write this as 3d10. And then our final component of the electron configuration to get to arsenic is 4p3. So let's scan our options and see if we even need to deal with these two noble gas electron configurations. And it looks like we don't, because we see that our answer matches that of response option E, which is our final answer. When writing chemical formulas for organic structures, it's best to first count out your carbons and hydrogens, and then you can add in any heteroatoms in your structure. So first, let's count up our carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can first write C9 as the first part of our formula. Then we can go ahead and write in our hydrogens. So for our methyl groups, we know we have 3 hydrogens. So I'll go ahead and draw those in. And then for the cyclical group here, we know that we can add 2 hydrogens to give each carbon a total of 4 bonds. And then we can check the rest of our carbons. The one with the arrow here already has a total of 4 bonds, so it won't have any hydrogens. The one to the right of it does have a hydrogen to give a total of 4 bonds, as well as the one above. And then we notice up here, the carbon with the carbonyl group already has a total of 4 bonds, so that's settled. So when we go ahead and add up all of our hydrogens, we'll get H14. And then looking for any heteroatoms, we see an oxygen. So then we can add an O to our formula, and our final formula for this structure is C9H14O. For this question, we need to determine which element has an outer electronic configuration of Ns2Np4 in its ground state. So we don't know what the N value is, but we know that each row of the periodic table is associated with a different value of N, denoting its energy level. So using different colored boxes, here our first box in red demonstrates our S2 block, or a full S block with 2 electrons. And then in blue, I will put the P4, so that means we have 4 electrons in the P block. And if our final electron is P4, that means that one of our options is in this column highlighted in orange. So if we scan our response options, we see that our final answer should be sulfur, which is option E. For this problem, we're asked to identify the correct electron configuration for nickel, which is element 28. So when looking at the response options, we see that we're given the noble gas configuration, which means you use the previous noble gas and the valence electrons leading up to your element. So in this case, the noble gas we should be using is argon. So right off the bat, we can cross off these 3 response options with krypton, because krypton appears after nickel, so we should not be using that. And next, let's identify how many electrons we have in our valence shell. So we should have 2 s electrons, and 1, 2, 3, 4, 5, 6, 7, 8 d electrons. So we should be looking at argon, 4s2, 3d8. So our final answer should be E. Now looking at response option A, this is kind of tricking us into thinking we have a D9. And let's recall that if we have a D9, this is unstable. And so we'll take an electron from the S, which would make it 4s1, but then we'd have 3d10. so it would become more stable. So response option A, we can just toss out. So our final answer is E.